Computer science has a profound measurement problem. When evaluating an algorithm, predicting the worst possible disaster is safe, but fundamentally pessimistic. Hoping for average, random inputs is optimistic, but mathematically fragile. We must confront the reality in between, a paradigm where rare catastrophic costs are strategically absorbed to guarantee long-term efficiency.
Let us draw a line between average and amortized truth. Average case analysis relies on probability. It tells you the expected cost if the input behaves nicely. But if reality deviates or an adversary attacks, the system collapses. Amortized analysis provides a deterministic reality. It guarantees the absolute upper limit on average cost over a sequence of operations, entirely immune to adversarial input.
To prove these absolute guarantees, computer scientists rely on three primary methodologies. First, the aggregate method takes a global view, dividing total sequence cost by the number of operations. Second, the accounting method acts like a banker, overcharging cheap operations to save credits for the future. Third, the potential method treats the data structure like a physical system, banking potential energy during routine, inexpensive operations, which is then spent to pay for major, expensive structural changes.
Consider the dynamic array. If we resize it by adding a constant amount of space, known as arithmetic expansion, we trigger the expensive copying process too frequently, resulting in a disastrous amortized cost of order n. But if we double its size geometrically, the expensive events become exponentially rarer. The math converges, proving a constant amortized cost of order 1. We prove this geometric efficiency using the potential method. We define the system's energy, phi of d, as 2 times the size minus the capacity. When the array reaches its limit, the stored energy peaks. The moment the costly resize operation hits, the system discharges this stored energy, paying off the computational debt instantly and maintaining a constant amortized cost.
This philosophy extends to self-adjusting data structures like Splay trees. Unlike rigid trees that enforce perfect balance at all times, Splay trees adapt dynamically. When an element is accessed, it is aggressively rotated to the root. This exploits the 80-20 rule. A small fraction of data is accessed most of the time. While one access might trigger an order n rotation cascade, the amortized cost naturally bounds to order log n.
However, amortization harbors a critical vulnerability, the assumption of ephemeral time. If our data structure is persistent, meaning past versions remain accessible, time branches. A user can repeatedly trigger an expensive operation from the exact moment before a resize, effectively double spending the saved computational credits. In an instant, the amortized guarantee disintegrates back to worst-case reality. To resolve the persistence paradox, systems rely on lazy evaluation. Instead of performing the expensive work immediately, it is suspended. When forced, it computes once and memoizes the result. This brilliant mechanism ensures that no matter how many times a timeline branches, the heavy computational price is paid exactly once, perfectly bridging functional persistence with amortized efficiency.
Ultimately, utilizing amortized complexity is an architectural decision about time. For compilers or batch processing pipelines, raw throughput is king, and occasional latency spikes are acceptable. But for real-time systems like medical devices or high-frequency trading, a massive garbage collection pause is a fatal flaw. In those high-stakes arenas, algorithms must be aggressively de-amortized, mathematically spreading the work across every frame to guarantee unyielding real-time execution.